This is the one that I talk about, the R critical, rho critical. Okay, so if you look at here, okay, here, so you see in option 1 and 2, the steel ratio will generally exceed this to restrain the crack width. Okay, so this is the one. That means you have to have at least this one. Okay, and that value is given in the book, but here I could not find readily in the code. Oh, right here. I think it's yeah. Table A.1, right here. Appendix. So this is the appendix. Okay, if you look at the appendix here, so this rho critical, okay, for grade 460 steel, this is 0.35%. Okay, all right. If just this is water tank crack control, so the water tank crack control is much more stringent. Okay, because the water tank, if the reason it is much more stringent is because, you know, if water seeps through, can cause corrosion in the rebar and so forth. That's why water tank, the reinforcement for crack control is higher, 0.35%. It's 0.0035. That means normally I call it 0.35%. Huh?
The steel area I calculate in
That means
one direction, or I need to calculate total of both.
No. That means this direction you need to have 0.5%. This direction also 0.5%. Okay. That means each direction we have at least. That means total is 0.5%. Correct, right? Percent. That means this direction, this direction, you need to have 0.25%, and also this direction you need to have 0.25%. Okay? Understand? Okay, so in the water tank, just for comparison, the water tank you will have to have at least 0.35%, which is higher than the normal one. Okay. So let's say how would I design for the horizontal steel? So how would I design for the horizontal steel? Let's say this wall here is 300 millimeter thick, right? Let's say wall thickness is 300 millimeter, and I'm going to use let's say T10. You can choose T12. Okay. Let's say I use two T10s, one in each face. Let's say I use 2 T10. So 2 T10, the area, total area, AS, will be 2 times 78.4 millimeter square. Okay, so what would be this? 156 millimeter square, right? Okay, all right. Now, then the question is 2T10 at what spacing, right? So at the spacing such that the reinforcement ratio is 0.25%. That means summation of AS. Summation of AS. This is the steel area, right? And then the concrete area. Concrete area is this one multiplied by this one, right? The spacing. Concrete area for these 2 bars, right? Is the spacing multiplied by the thickness. And this has to be more than more than or greater than has more than or equal to 0.25%. So then I go and calculate the S. So S I move over here, 0.25 I move over here, right? So if I my S excuse me, as I move over here, then what I will have is my S is less than or equal to, right? Summation of AS divided by 0.25% divided by the thickness. Okay, so the summation of area is 156 millimeter squared. The thickness is, let's say, 300 millimeter. And here, 0.25%. 0.25%, that means 0.25 divided by 100, right? Okay. By the way, did I tell you what percent means? Percent. Why percent is per 100? When we say 5%, it means 5 per 100, right? Correct. 6% is 6 per 100. Percent, basically it comes from the word per century. 1 century is how many years? 100 years. So that percent, that cent is from century. Okay? Alright? So that's why when I say 0.25% is 0.25 per 100 divided by 100. So what is the value here? Can you calculate it for me?
208.
So, this is equal to, you say it's 208 millimeter, right? Right? Okay. So what does it say? It means this is less than or equal to 208. Yeah.
Can I use the AS, right? I use the area of concrete. I use 1,000.
1,000 also can, but 1,000. So if you use 1,000, then you will have how many bars?
Then
Because you do not know how many bars to put in yet.
but
Correct, right?
I know the diameter.
Huh?
I know the diameter.
You know the diameter. Diameter of what?
The bar that I want, so I can find the spacing.
So that you want to find the spacing. What do you mean?
就是我们 assignment 做下来的时候，我们 assignment 是直接拿1000嘛，直接一个。
Okay, but anyhow, it means you would use spacing, let's say 200, right? That means 2 T10 and 200 you satisfy, or you can use 150 also can, right? But it has to be less than or equal to 208. So 208 normally we don't do 208 one. Either we 205 or 200. We try to jump by. Okay. Alright. Main thing is because we only have one equation. This is our design equation, right? This design equations we have two unknown variables. One is summation of AS. The other one is the spacing. Right now. So before you design it, you do not know you have to basically choose what size of bar you use and what spacing. Right? So you have two variables. So, but you only have one equation. So how can you solve two variables in one equation? So you have to fix one of the variable first. And I say, okay, I'm going to use T10. You can use T10, T12, T8, T16 or whatever. Right? So you have to fix that one first. Then you choose the spacing. Then based on T10, what's the spacing? Okay? Or you can reverse. You can say, okay, I want to use a spacing, or let's say 150. What bar size should I use? Should it be T8? Should it be T whatever? You see what I'm saying? Okay. So normally I would choose a bar size first, because my bar size is because normally either T10 or T12. Okay. Very seldom we go to sometimes you go to T16, it's really very thick. Okay, all right. So normally our retaining wall quite thick, so we will put two layers. If let's say your wall is, let's say 125, let's say, or 100, normally you just put one layer only. Okay. So normally the idea is I would say normally people would put, very seldom would put one layer on, because only very thin, let's say your wall is 100 or 75, then you put one layers. Because if you took two layers, there's not enough spacing, plus the concrete cover. Because your concrete cover, let's say for this concrete cover, let's say for water tank, 35 is already 70, right? Concrete cover is already 70. So you put two layers plus another spacing, that exceed almost 120 something. Okay, so all right, okay, huh? Okay, so all right, okay. Okay, so this is the earth retaining wall design. In summary, this is the wall. So I've already gone through how to design. Okay, so if you are really an experienced engineer, when you look at the thickness, when you look at the when you look at the height, right? An experienced engineer, okay, because normally our sequence of work is this: you design, you come up with the results, and then you ask the drafter to draw, right? Ask the drafter to draw. So it's sequential. So the drafters probably would not able to draw, right? Before you finish your design. Okay. So an experienced engineer like me, in order to gain time, we have to do it parallel. That means I know the wall. I just tell the drafter, say, okay, this one you take T20 at 200. This one you take, let's say, T8 at 200. The horizontal you take T10 at 200. You go and draw. Okay. Then at the same time I design. I check my design. Okay. So if you are very experienced enough, your initial estimation is close to your design estimate, your design results. Okay, so so that is normally when, let's say, if you have been to working in consultant, actually consultant, they want the design. Okay, let me tell you a story. So last time I used to do freelance consulting. When I was teaching here. So my previous company would call me and say, okay, we have a project, right? So our office is short-handed. Can you help us to design this and so forth? So I asked him, when do you need it? Okay. So he hesitated a little bit. So I said, when do you need it? Hesitated. I said, then I told him, you must have needed it yesterday. That's why he was very urgent. Okay, so in the office, in the consultant office, time is always a critical element. So sometimes, in order to gain speed, we have to do things parallel. The design and the drafting done at the same time. But of course, you must be able to confident that the design that you tell the drafters to do is quite accurate. Okay, so as a senior engineer, or sometimes you must develop that kind of ability, lah. Okay. All right. Now, I'm going to talk about the base, how to design the base, because you cannot just say design the wall without designing a base. It goes hand in hand. But as I say, the design of the base is more complicated. I'll just tell you the approach to do that, okay? And so you'll not be tested on the base, on design on the base, okay? But you need to know. So then when you go out to work, at least you know, even though you have not been tested, at least you know what to do, okay? Now, the other thing is this, okay? ，okay. Now this one, I couldn't see. Let me see whether I can take it. Okay, now there is actually UK. There is a center called a Concrete Center. So they have developed these spreadsheets. I think a lot of consultant firms has it. So these spreadsheets to ES 8110, etc. So advisory group grade 1. So retaining wall design to ES 8110. Okay. Idealized structure, and so they design. So this is already put in a spreadsheet. All you need is to actually enter these values, okay, and it will speed up the reinforcement detail. So, okay. So they can do the stability design. They can do the design of okay. Okay. They can do the analysis design for you, etc. And you see the vertical external face, what's the rebound, what's the center, okay? Vertical internal face, transverse, okay? So vertical external face is this one, this one. Vertical internal face is this one, and transverse is this one, okay? Understand, huh? So over here, that means if you have this spreadsheet, all you need to do is just to key in the input, and then the output will give it to you. Okay, but the thing is here, we want to teach you the theory first. Okay, you know what is the theory behind it. Okay, how do they calculate this? Okay, so if you here, if you look at these. Okay, so okay, here they even put in the water table, assuming that there is no water discharge. Okay, the water table could be here, could be here, could be here. So you have to give it a HW. Okay, all right. Okay, so if you don't have a water table, that means we assume that the water table is way below there and that has no water. Okay. So here you can see the surcharge. Surcharge. Okay, surcharge here. So this is the lateral pressure due to the surcharge, which is in the middle, right? This is the lateral pressure due to the soil. Okay, due to soil. And this is the lateral pressure due to the water. Okay, all right. So here you can see earth, surcharge, and water. Okay, so that's why I think if you have this spreadsheet, okay, I mean, it becomes very easy. You just key in the input only, wall thickness, what is the height, and then you get the results. Okay, all right. Okay, so, but the thing is over here, teach you the theory. That means you understand how these things come up. Okay? Over here, of course, they calculate the, for example, the design angle of internal friction 30 degrees, okay, and so forth. So this actually to help you calculate the Ka, the active soil pressure coefficient. Okay, in a test I'll tell you what Ka is. Okay, in a spreadsheet, I mean they start even further because Ka developed from your cohesion and adhesions and the friction effect. Okay, all right. And also they also have the spreadsheet to do the pad footing design. Okay, to do the pad footing design and also the also the parquet. A lot of when we started working out, we actually write our own spreadsheet to automate the calculations. Okay. All right. Okay. So this is here. So I'm going to round this one off. Now, at the very beginning, I say that in order to design an element, we need to know what are the loadings acting on the element. Okay. And from there, we calculate the shear diagram and the moment diagram, right? And so forth. Okay. So based on that, we need to know what is the base slab, what is the loading acting on the base slab. Okay. Now let me start up with the most simple slab, footing slab, right? So let's say I have this one. This is a column loading, right? Column coming down. Okay. So this slab here definitely has a column load acting on it. Besides that, it also has a soil reaction acting on it, right? Correct? Soil reaction. So basically, this is kind of like a cantilever slab. The base is actually kind of a cantilever slab because when you apply this one, it's deflecting like this. Because this thing pushed this thing up, right? Okay? So this is a cantilever section, these are cantilever sections, and this cantilever sections has a uniform load, right? Right? Okay. So that means you design this as a cantilever slab subjected to a uniform loading acting upwards. Okay, that's how you design, right? Okay. Then your reinforcement, of course, tension reinforcement would be at the bottom, right? Would be at the bottom. Okay. All right. Now this is the simplest. Okay. When I say simplest, because it only has vertical loading, but sometimes the loading can carry moment. The column can carry moment. That's fixed end base, right? So what you do is now you have this, and then you have this, the moment. Then you also have the soil reaction, right? But your soil reaction in this case is not uniform anymore, right? Because this one, when you apply the column load, okay, you will have uniform pressure. But when you apply when you apply a moment, okay, the pressure diagram will be like this. Okay. Let me draw. This one is the uniform pressure caused by the column load, right? Yeah. Now, here, let's say this is a bending moment. So the bending moment will cause a pressure diagram like this. A pressure diagram like this. Okay. This is the stress diagram of a bending moment, right? So if you add these things together, this, okay, let's say let's say this is 10. This is 10, and let's say this is 5. This is 5, and this is 5, right? So now your compression here will be 10 plus 5, will be 15. And over here, compression, this is tension, right? They will be 5. So now you have a pressure diagram. You have a pressure diagram that looks like this. You have a pressure diagram like this. This will be 15, and this will be 5. Okay? Because here is compression, here is tension, they cancel each other, right? Okay. And if this one is getting bigger and bigger, let's say this is 10, this is 10, then your pressure diagram would be triangle. Triangle. Because if, let's say this is 10, this is 10, then they cancel each other out. That means here is 0. Understand? Okay? Alright. So you can have this pressure diagram, you can have this pressure diagram. What happens if this one is greater than 10? Then your pressure your pressure diagram will be a triangular, but like this. Because the soil cannot take tension. Okay, you have to remember, the soil can take compression. The soil cannot take tension. Alright? Yeah. Now, let's say we have this pressure diagram. Right? Then what you have is, this is still a cantilever section, but subjected to a trapezoidal load. Not a uniform load. It's a trapezoidal load. Okay? Same like over here, also subjected to a trapezoidal load. Okay? So this is, that's why I say, in order to design the base, you have to understand what are the loading actually acting on the slab. Okay? From the top and from the bottom. Okay? Now, okay, when you look at the slab, okay, what are the loading acting on the slab from the top? First, you have the soil weight, right? Yeah, this soil is sitting on here, right? And also, you have the wall weight. Okay. Also, you have this bending moment. Okay. So that means your base, you have base. You have the uniform loading from the soil, right? And you will have a wall weight, vertical wall weight, as well as this one, right? Okay, so you have, so it's much more complicated, okay? Because this is offset, not in the middle, and this is partial, okay? Now, and this moment and so forth, and then you have to calculate what is the bearing pressure on here. Okay? And most likely the bearing pressure, there will be more compression here than here. Okay, because I have a bending moment like this. So let's say I use a red color to show the So you have this loading acting on the top on the slab, and then the soil pressure pushing up on the slab. Okay, so let's say in this case, this is a trapezoidal soil pressure, and I'm assuming that you have learned in you know how to get this bearing pressure, right? Okay, then this is the wall, right? So the wall, we have two parts. The wall actually breaks the slab into two parts. This one here is called the heel. The other one is called the toe. Just like a foot, right? So you have the heel here and the toe. Okay, so this is the, depends on how you want to see it, right? So if you look at the whole example, so if you look at here, they have the toe, and then here the toe, here is the heel. Okay, so so these calculations is actually for this problem. For this problem. Okay, this is the toe, this is the heel, this is the front side, this is a back side. This is kind of like a foot, right? Alright. Okay. So here they have calculated the pressure diagram to be a rectangular trapezoidal pressure diagram. Okay. Then, just like earlier, you will look at this. Right? This segment here. This segment here, you have a soil pressure acting here and a loading acting here. So based on that, that means I will. So this is the toe, and this part here is the heel. Okay. So if you want to design this part, you just look at this part here as a cantilever beam subjected to a downward loading of this uniform soil weight and also this upward pressure. You get the moment here. And then this one here, you also get the moment here. Okay? Now, this one, this normally is quite short. So is 800. Over here, this is 2002. Okay. Now, let me ask you, when I design this, when I design the toe, right, my rebar should be placed at the top or at the bottom. My structural rebar should be placed at the top or at the bottom. Should be placed at the top or at the bottom? Huh? Okay. So here we say a T12 at 200. Okay. He point at the bottom. Why at the bottom? Because here you have this one pushing it up, and you don't have this much resisting. So this one is actually bending up like that, right? So bending up like that, that means the tension is on the bottom side. Okay, understand? Here, because here is relaxed. Normally this one here is much bigger than this one. So here your tension side is on the top. Your tension side. And because of this is much more cantilever, much longer, so you can see that it's a T20 at 200 as compared this one is T12 at 200. Okay? Understand? So this is the basic concept. Alright? First, as I said, you understand what are the loadings acting on the slab. You have here, this is the self-weight from the soil, right? And here is this point load here is the weight, self-weight of the wall. And here is the bending moment due to the lateral pressure. Okay, so based on this, you calculate what is the soil diagram here. Okay, okay. Most likely is trapezoidal. Okay, sometimes we very rarely, only one or two cases I encounter. This is a triangle. Okay, then based on that, now you know what are the reactions, what are the loading acting on this. Okay, then you design for the toe and design for the heel. The toe and the heel basically are cantilever elements. Okay, cantilever elements. So you design for the cantilever movement here, cantilever movement here. Okay, all right. Then so that's why we have top reinforcement basically coming from here. This one coming. Okay, all right. So actually this is easy to calculate, right? This part here is harder to calculate. Okay, but once you have this one, then you calculate the movement. Right? So the base slab, you have the top reinforcement, the bottom reinforcement. The bottom reinforcement basically carrying the bending moment, the upward bending moment from the toe. Okay, this one is carrying the downward bending moment from the soil. Okay, and then this one going in, temperature control. Okay, alright. So, as I said, I think I have taught this course for more than 10 years now. I think only once did I ask the students to design for the slabs. But I give them the soil diagram because if I don't give them the soil diagram, I think they won't have enough time. Okay. Okay, all right. So to summarize, to design for the retaining wall, okay, we need to design for the stem and for the base. Okay, all right. Stem and the base, okay. The stem and the base, you have vertical reinforcement as well as horizontal reinforcement. Okay. The question is how much only, right? So when you look at this design, here they say T20 at 200. Looking at this one, right? T20 at 200. Okay, but the rest they didn't give you. They show it to you, say that okay, we will have rebar there, but then they didn't tell you how much to put in. Okay, all right. Same thing here. They design. In other words, they only design for the structural reinforcement. Okay. Okay, so we have roughly half an hour left. So I will, in a canvas, I have not posted up this material yet. So I think in a book, you have all the electronic books, right? Basically, that is coming from electronic book, chapter 11. So it's better you look at the book, okay? All right. Okay, then I will post up one assignment for you to practice on. Okay, for you to practice on. And okay, we will come to the last topic. Okay, the last topic is shear wall design. Okay. Now, the shear wall design will takes a little bit long time because I mean the shear wall design itself is rather simple, but the thing is, the loading acting on the shear wall design is coming from the wind load and earthquake loading. How do I get that wind loading? How do I get that earthquake loading? That is a big part, a big knowledge there. Okay. So I will probably start from the wind load first. Okay. As I said, I try to finish the lectures in week 13. So week 14 is revision, or at least I will devote, I think, 1 or 2 lectures to review what is for the final exam. Okay, all right. So I try to finish all the materials in week 13. Okay, so that I think some of you also quite busy at the very end. Right. All right. So I try to finish the lectures on week 13. Then week 14, at least you can devote your time to. Okay. All right. Okay, maybe
Dia kayak udah selesai kan? Oh, for this chapter, okay, we continue. Continue.
okay. In Malaysia, because we don't really have earthquake hazards, which is very different from Indonesia. Indonesia has earthquake hazards, right? So that's why in Malaysia we do not teach so much about earthquake engineering. Okay? We basically our lateral loading mainly coming from the wind. Okay, coming from the wind. So our starting point is a BS 6399. Okay, 6399 Part 2. Okay, Part 2 is called a practice for wind loads. We also have 6399 Part 1. Part 1 is for what? Part 1 is for your knowledge. Part 1 is called a practice for dead load and imposed load. Okay, so in this Part 1, you learn, for example, a hospital floor should design for what kind of loading. A parking space should design for what kind of loading. A sports facilities, what kind of loading? Because different usage will have different design loading. Okay, all right. For example, a residential area, we have a lighter loading than a stadium. Because stadium are more crowded, packed, right? So this is given in Part 1. All right. Just to show you the imposed load. Okay. Imposed load means live load. Okay. live load. So here you can see type of activity occupancy for part of the building or structure. Let's say domestic and residential activities, right? Okay. So we design for uniformly distributed load of 1.5 kilonewton per meter square. Understand? Because these are given in what? These are given in floor loading. Floor loading is kilonewton per meter square per unit area, not per unit length. So what you have been doing in the beam design is kilonewton per meter, isn't it, right? Right. But when you go out to work, they tell you, okay, the superimposed load use what? They are all in terms of kilonewton per meter square. Okay. So, for example, bedrooms and dormitories, except those in hotels and motels. So this is 1.5 kilonewton per meter square. Bedroom in hotels and motels or hospital wards, toilet areas 2.0. Okay. Billiard rooms 2.0. Communal kitchens except in flats 3.0. Balcony 1.5. So different area we have different loading. Okay, so this is a British code. Now, I have used the US code before, Australian code. They are actually quite similar. Okay, in terms of the imposed load. I think in Indonesia, I think they follow more of the American standard. Okay, because British standard do not really have much. In Asia countries where they are earthquake, normally they follow the Americans one, because the Americans are quite outdated in their earthquake engineering. Okay. And that is another source, of course. The big earthquake countries, the big code is in Asia, Japan. Japan is a lot. Okay. China. Okay. And in Europe is, for example, countries like Italy. Okay. Normally, Germany, Switzerland, they don't have much earthquake. So most of the European earthquake ECA is actually from the Italian. Okay, from Italian. All right. Okay. So, and all these countries, Japan, US, they have joined working group. Okay. So when we were students, what happened is, let's say for example, there's an earthquake in Japan. So the Americans should send a team, engineers, to go to Japan, and they will look at what are the buildings are being damaged, okay, and why are these buildings being damaged, and they look at some older buildings are not. Then they try to update the earthquake loading, okay, because each earthquake, okay, are distinct in nature. They are not exactly the same. Okay, so that is why every time in America, of course, the Alaskan earthquake, the California earthquake, then you have Mexico earthquake in Chile. You know, those are the big areas. Those are the big areas. Now, having shown you ESA 6399 Part 1, then as I say, this is Part 2, okay, for the practice for Windows. Now, previously, we in the older generations, let's say people who are 15 years, even at least more 10 years older than me, they would use what they call CP3, Chapter 5. Okay, the older generation, they will talk about CP3. CP is concrete practice. Concrete practice, Part 5, Chapter 5, basic data for loading of buildings for wind load. Okay. Then this is replaced by 6399 part 2. So the wind loading, the starting point is what? Where is the starting point for wind loading? Yeah. Let's say if you want to investigate wind loading, right? You want to calculate wind loading. What is your starting point? Wind speed. Wind speed is the starting point. Zero wind speed, that means no wind loading, right? Okay. The higher the wind speed, the bigger is the wind loading. Okay. Now, the force due to wind loading, okay, is not proportional to V. V is the velocity. It's proportional to the square of V. But what does that mean? That means you double the wind speed, you quadruple the wind force. That is called square. Right or not, right? V squared. So if you double the wind speed, the force will be 4 times more because it's 2 squared. Okay, so that's why the wind speed needs to be as precise as possible. Because if it is proportional, then you know it's still manageable. But because it is to the power of square. Okay. Now, why is it to the power of square? Why is it to the power of square? Huh? No. Okay. Why is the wind force? Why is the wind force proportional to the square of the wind speed? Because we are looking at the things from the energy point of view. The wind speed gives you the kinetic energy. Okay? The kinetic energy is 1/2 of mv squared. Kinetic energy, right, is mv squared. Okay? And then the wind force is actually, you can say, is a pressure energy, which is the potential energy. Okay? So this is very much like if you study hydraulics or fluid mechanics. You study, what do you study? You study the Bernoulli principle. Right? Bernoulli principle is energy, kinetic energy and pressure energy. Okay? Alright? So that is why it is proportional to the square of the speed, not the square, not V, just V itself. Right? Huh? So the question now is, where do we get the wind data? Where do we get the wind speed? How do we measure the wind speed? Now, the wind speed is a very complicated thing. Okay? Because let's say in T here, right? Okay. Let's say the wind speed, for example, let's say the wind speed here is at this level is depends on, okay, there are different types, ways to measure wind speed one. But let's say the wind speed is, let's say is 30 meter per second. Over here, 30 meter per second. Okay? At this level. Okay? Okay, okay, I want you to think. Let's say this is in T, right? This is our building and so forth, right? So and so forth, yeah, here, right? Let's say the wind speed here is 30 meter per second. Okay? Now, at the same location, if you take it 100 meter up, or 200 meter up, 300 meter up, what do you think? Is the wind speed going to be the same? Same location. Okay? So that means the wind speed also depends on the height. Right? The higher, the taller the building, you probably feel more wind. Maybe you go to the higher, right? You feel more wind. Because there's less obstruction. Okay? So the wind speed depends on the height, and the wind speed depends on the time. At night, morning, different, right? 11 o'clock, 12 o'clock, 13 o'clock could be different even at the same occasion, right? So if let's say I measure the wind speed here, I measure from day to night. I measure in January, measure in February, measure in March. They are going to be different. Okay? Then the question is, there are so many values, but which is my design values? Correct? Let's say you are design.
Fix one average.
Huh?
Fix the average.
Take the average. Okay. The wind also have what we call a gust. Okay. What do you mean by gust? Gust is sometimes suddenly the wind is right. So this is a sudden gust. Okay. Now when you take an average, right? Let's say 50. Average is 50, right? The maximum could be 100 and 0. And you design 50, what happens if this 100 comes?
Even the maximum.
You try to design the maximum. You cannot say design for the average. Okay, so I think we will stop here, but these are the points that I want you to think. It means wind speed is not so simple. Okay? Alright? It's 1:39. Actually, we still have some time, right? But I think some of you are expecting.
Sebenarnya kita masih ada waktu, tapi saya lihat kalian sebagian dari kalian udah pergi.
Huh?
Let's go.